This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hello, and welcome to another episode of Design Safe Radio. Glad to have you here. I'm your host, Dan Zahner, and looking forward to chatting with my good friend, Dr. Jeffrey Berman from the University of Washington. And he is one of the co-PIs with our NHERI Tallwood project, which we've heard a little bit about from a couple of folks on our show the past year or so. One thing that we're doing for those of you who are watching on YouTube, he has in the background there our 10-story building that is being built right now at the University of San Diego, large outdoor shake table. And if you can spot the NSF logo, whoever spots it first and says where it is in the comments, we will pin your comment. So starting a new thing with that. Thank you, Jeff, for giving us the opportunity to have some fun on YouTube. So Jeff, welcome. Good to have you here, man. Good to see you.
Yeah, good to see you, Dan. Thanks for having me. It's an awesome opportunity.
So tell us a little bit about yourself and kind of where your research interests are, because you've got quite a few different rabbit holes that you're involved in. But just, tell us a little bit about yourself.
Yeah, thanks. So I'm a professor at University of Washington. I'm in the civil engineering department. I teach a lot of structural engineering courses. And the research area, I started my career kind of in steel structures for seismic loading, and spent a bunch of time there and got really into the notion of design for resilience and design for damage control and repairability in steel structures, and have since kind of branched off into a few different areas. One of those is taking some of those same concepts and porting them over into the mass timber building world and that whole movement, which is how my collaboration with all of the co-PIs on the Tallwood project began. And then also I am also the operations director for one of our NHERI facilities, for the rapid facility here at the University of Washington that does a lot of we have tools for natural disaster reconnaissance and data collection post-event, and I've got a lot of interests in those areas, what we can learn post-disaster. I also have, I'm kind of an earthquake engineer in general as well. And my colleague, Mark Eberhard, and I here have done a lot of work on Cascadia subduction zone hazards and their impact on the Pacific Northwest. And
yeah, one of the things it's just always fun to talk to you, because I think we're similarly wired in the multi-passionate sense. You've got a lot of different things that you're very passionate about, and it's just always fun to talk about them. So let's dive deep into Tallwood today. So
Sure.
We've talked about it a little bit. It's a long-term National Science Foundation funded research project, started 2015-ish by my recollection, but a lot of moving parts, literally and figuratively, hundreds of researchers, lots of different industry groups. So, and as a co-PI, you've been involved since the get-go. What are you guys hoping to learn from shaking that 10-story building on the world's largest outdoor shake table? What kind of impact might this have on engineering and resilience on the built environment?
There's a really significant industry academia partnership. I think they are becoming more and more critical, more and more important to push some of the solutions and new ideas that we come up with within academic research, to push this to practice kind of faster and more effectively for industry.
Because usually it takes, a decade or more to push research to industry in most cases from our natural hazards research. Yeah.
Right. And I think this project in particular, it's been such an excellent collaboration between researchers and between kind of academia and industry. We've developed these new technologies, not kind of in a in a vacuum in academia. We've actually developed them kind of hand in hand with industry. You know, Simpson Strong Tie is such a huge partner in this project. They have drift compatible connections for beam to column connections that are implemented in the 10-story building, and we helped them design. They designed them. It's just a fantastic partnership.
Mm-hmm.
There's so many kind of facets of this project that could not have been achieved with an academic only team. We have built now. I can say we have built because we topped out right before the holidays.
Yeah.
Yeah, and so we have built a 10-story building on a shake table, and I can tell you, the Kopiais, who are fantastic researchers, none of us really have experience with constructing 10-story buildings.
No, yeah.
So, having that partnership, we couldn't do a project like this without them. And, I think and it's been kind of through every aspect. We have a great partnership with a architectural firm and structural engineering firms who are leaders in the push of mass timber into real projects, not just on the West Coast, but kind of all over the country. And they helped design the building. They helped guide what would be the practical details, while still making sure that we had the innovation. Because it's still academic research. So
yeah, because your responsibility as the scientific team is,
yep,
what is that big research question and how do we answer that? And that's what the NSF is funding you for, right? And normally the NSF doesn't get into the innovation game of technology development. And this is, I think, fairly unique in research, this project that you put together, that it satisfies scratches the NSF itch of that fundamental science, but also gives real world practical application fairly quickly.
Yeah. And there's so many, there's a few kind of really big research questions that we're answering, but there's so many, great research questions that we'll be able to look at with the data set from this test.
Yeah. So what are some of those research questions that you're hoping to tackle here?
Yeah. So I mean, this is one of the first, certainly at this scale. This building was designed with a resilience design approach. So the post earthquake resilience of the structure was evaluated and was used to change design decisions to make, to both assess the design and then actually make some tangible changes to the design. So there's a resilience-based design framework that's been developed with John Vandalen, one of the co-PIs. That's kind of been his thing. And so this building is an opportunity to say, how does that work if we really, because we don't have a resilience-based design approach that's kind of out there in practice being used for lots of buildings, and then there aren't any earthquakes that are going to come and test those buildings and determine whether or not that approach makes sense and delivers,
knock on wood,
on its promises. And so this is a real opportunity to do that.
So can you give us a little bit of a peek behind the curtain into, when we say mass timber, what that means?
Yeah, well, there's this 10-story building has just about every type of mass timber that you could have that is currently made in it. So the walls, there's two types of shear walls in the building. One type is mass plywood panel, which is those types of veneers like you're talking about, layered up and glued together. And then the other one is cross-laminated timber, which uses 2x4s, 2x6s, depends, kind of laid out. So kind of long direction, one for one layer, and then a cross lamination for the next layer. And they're able to build up big sections in that way. You can kind of see behind me a splice connection. So each of the wall panels is actually about 3 stories to 3.5 stories tall, which is, really interesting. That's about as big as we could get delivered to the site on a truck. And yeah, and then and each one is actually has details that were cut into it using CNC, computer numerical controlled fabrication processes. So they show up to the site almost completely detailed, and then you're able to just essentially take it off the truck and stand it up. And then begin, constructing the rest of the building around it.
Very different from a steel and concrete building where you're site building just about everything.
Yeah. It's similar, maybe more similar to steel than it is to concrete, and that, components come generally fabricated. But we're not pouring any floors. All the floors are mass timber in the building. Again, different types of mass timber. The beams and the columns here are all LVL, laminated veneer lumber. Such amazing industry partners. They have donated so much material for this test. So shout out to Boise Cascade for the beams and the columns. Shout out to Barrel mass plywood for the mass plywood panels. Just amazing, the support that we've gotten. But then every floor system is there's 4 different types of floor systems in the building. There's dowel laminated timber, nail laminated timber. There's what we call GLT, glue laminated timber, which is kind of similar to CLT, except you're stacking the boards up kind of next to each other.
Like a big cutting board, sounds like.
Yeah. And then there's some CLT floors as well. Just really amazing opportunity for kind of all of our industry partners to come and bring their products, some of them that are not currently recognized in IBC. And so this is an opportunity to provide some data towards, code acceptance of some of the individual products. So great opportunities, and everyone should visit the Tallwood website just to get the complete list of industry partners, because it's really long. Mention them all here. So
you got that big rocking wall behind you, and we've talked about it a little bit. What actually is a rocking wall? Like, let's nerd out a bit. Why is this useful? What does it do? And then how does it work? You've got sections that are 3.5 stories tall, leads up to 10. How does all that work?
Yeah, so the concept is pretty simple, and it's not a concept that we developed. It was actually developed for precast concrete construction back in the 90s, and one of my colleagues here at UW, John Stanton, was very heavily involved in that work. But so the idea is kind of similar to what they were doing there. Obviously, the materials are different. Some of the energy dissipation, some of the localized behaviors, and the way we detail things and model things are quite a bit different. But conceptually, it's not super new. And the idea is that you don't rigidly connect the wall to the foundation. Instead, it just sits there and is post-tensioned with steel bars, in this case, that they will go from the roof to the foundation, and then the wall is allowed to uplift. So you can see the steel bar, the steel post tensioning that's running from the roof all the way down to the foundation. All these
guys there.
Yep, those big long bars. So those act like essentially big rubber bands. They allowed the wall to uplift. And what that does is reduces the damage at the base of the wall. So you don't have damage from tension at the base of the wall. You have the potential for some damage from crushing and compression at the base of the wall, but most of it is, oh, there you go. And this is from
This is from like 2017 or 2018, something like that.
Yeah, exactly. So this is from the first round of testing that we did, what we kind of proof of concept testing on a two-story building on the UCSD shake table back in 2017. And you can see the wall kind of move relative to the floor, and that's the idea there. And so this allows us to design essentially a damage-free structural system that can accommodate really large deformations. So we can accommodate big drifts that are imposed from really big earthquakes and have very limited damage to the structural system. There are some steel energy dissipation devices that are incorporated into the design that are replaceable. Quickly replaceable.
Oh wow!
And that's part
these
of the
guys here, right?
Space design philosophy. They're in those little cutouts. There's some U-shaped steel components that are in there that are designed to be replaced should they need to be replaced. If they develop fractures, things like that. Super interesting thing about this test, and what really hasn't been done, is that this wall is 10 stories tall, and it has a first mode period of about 1.7 seconds, 1.8 seconds.
So what does that mean?
So for those who design taller buildings, they'll get that. That's a pretty long period, which means it has a pretty long kind of resonant period for lateral loading as it kind of sways back.
So it's kind of like the biggest string on a bass guitar. Like it's got a very low
exactly
resonant frequency.
Exactly. But what we think is really important, at least what the numerical models show is really important, and what previous kind of computational research has shown for rocking systems, is that when you get to taller walls like this, the higher modes contribute a fair amount to the response and can actually drive the maximum moment demands and shear demands in the wall itself. Actually, the biggest moment demand in this wall is around story 4, which is important because that's also where some of the splice, near the location for the splices that splice the wall panels together. So that was considered in the design for those splices. So this will really be one of the first tests of a building of this size, whether it has a rocking wall or not, where higher modes contribute that much to the response of a very non-linear system. And so it's going to be really, really valuable for us to take all this data that we're going to get from this test, analyze it, compare it with computer models, and then share it, of course, on Design Safe with the rest of the community to let everybody take a stab on, understanding how higher modes in taller structures that have a lot of nonlinearity, a lot of nonlinear behavior, in this case concentrated mostly at the base, how those higher modes, actually pop up. So, it's just going to be an amazing data set.
Yeah, and kind of to that point, one of the great things about having a network like this that has such great partnership with industry and the NSF and everything is data reuse. I mean, the amount of data that you're going to be putting out from this is titanic is probably a good word for it.
Yeah, huge amount of data. It's going to really be an amazing data set. We have every instrument location marked in a 3D Revit model as well. So data reuse is going to be just amazing for this. The data reuse opportunities. I think, our goal is in maybe 10 years, people are still writing papers with the data from this test and still learning new things about the seismic performance of just generally tall buildings and long period structures subjected to really large earthquakes.
Follow along with Jeff and all the whole project team at the Tallwood website, which we'll have a link for in the description. And you saw a screen share of earlier. So if you're not watching these on YouTube and are just listening on your phone or in your car or something, definitely check out, especially now that we've got these big tests going on that are visually exciting. We're putting these all out there and making sure there's a lot of great resources visually on YouTube. So check it out there. And looking forward to sharing more about Tallwood project as it progresses over the next few months here. So thanks again, Jeff, and we'll see you again soon.
My pleasure, Dan. Thanks for having me.
Thank you so much for listening to this episode of Design Safe Radio. We really appreciate it. Smash that like button if you're watching this on YouTube. Hit that little subscribe button. That really helps us out and bring this message to more people who are interested in hearing about how our engineers and scientists are making our society more resilient to everything nature throws at us. A big thank you to our sponsors at the National Science Foundation. Our award number is 212-9782. And a big thank you to our program officer, Joy Kowski, who is excellent. And our team at the National Science Foundation's Network Coordination Office for NHERI. Marty LaChance is our question writer and copy editor extraordinaire. Raquel Ruiz manages all things technical and editorial. And Morgan Glass is our social media coordinator. Big thank you to everybody at the NHERI NCO and all of our experimental facilities. Thank you and have a great day.